in this lecture, I'm going to count two things to analyze algorithms. I'm going to count how much arithmetic they do, the number of flops, floating point operations, and also how much they communicate. And communicate means moving data either between levels of memory hierarchy, DRAM and cache, or between L3 and L2 cache, all those different levels, or between different processors over a network. They're all expensive. And so what I'm going to do to analyze my algorithms to convince you that they're optimal in a certain sense, I'm going to count the number of flops they do. I'm going to count the number of words they move along any one of those wires in the last slide. And I'm going to count the number of messages they send. So what's a message? That's a bunch of words packed into one contiguous block that you move all at once. Those depend on the algorithm. Then there are three hardware parameters: the time per flop, the time per word moved, which is reciprocal of the bandwidth, and the time per message. That's called the latency. And those last two terms are the communication. Now, what's the hardware fact? These three hardware terms are orders of magnitude apart. The time per flop is much, much less than the time to move one word, and that's much, much less than the time to move one message. Not only are they very, very far apart, they're growing apart exponentially because of technological trends. So this is a little bit old, but people have looked at this data. It's sort of Moore's law-like data more recently. So the time per flop, thanks to Moore's law, which isn't quite dead yet, is improving at 60% a year. Everything else is getting better, but much, much more slowly. In fact, the latency of the network hasn't really improved very much since the Cray T3E, which is, how old is that machine? And so even if so what this means is that even if your algorithm is not communication bound today, it probably will be next year or the year after that. So we want to avoid communication to save time. But that's not the only reason. Here's a plot of the energy it takes to perform certain basic operations on a machine. So one double precision floating point operation, moving data between registers, moving it 1 millimeter on the chip, moving it a little bit farther on the chip, and then moving it off the chip, say to DRAM or to the local interconnect or across the system. The vertical axis is the amount of energy it takes to do that on a log scale, in picojoules. So in today's technology, or maybe it's yesterday now, 45 nanometer, it's 1.5 orders of magnitude less energy per flop to do a flop than it does to go to DRAM. And everything's getting better. The predicted costs in energy in a few years in 11 nanometer technology, everything will use less energy. Everything's going down to the red bars. But now there's a 2.5 orders of magnitude gap in energy. So whether you're worried about the your cell phone, the battery in your cell phone dying, or the $1 million per megawatt per year that it costs to run your data center, you care about minimizing communication to save energy. Okay, so that's what I'm going to be talking about today. So here are the goals of the talk. What I would like to do is redesign algorithms to avoid communication, to do less communication between all possible parts of the machine, between L1 cache and L2 cache, between L2 and DRAM, L2 DRAM in the network. And actually what I'd like to do is prove lower bounds, that no matter how you implement a certain very large class of algorithms, there's a lower bound in how much communication you have to do. And so I'm going to tell you what those lower bounds are. I'm going to compare the current algorithms that have been standard for many, many years, and they usually do orders of magnitude more communication than necessary compared to these lower bounds. And so we've been very busy inventing new algorithms, even for basic things like matrix multiply, which do much, much less communication and get very large speedups. And so that's going to be the source of the talk. Now, I don't have time to tell you about this everything, so let me just put up one slide with a few example speedups that we've gotten, and I'll go into more details in a few of them. So up to 12x faster for matrix multiply on an IBM BGP, so it's sort of surprising that you can get a 12x speedup for something that's been studied so well for so long. Tensor contractions are very similar to matrix multiply, so there's a 3x there. All pairs shortest path, that's a graph theoretic algorithm, but it still smells like 3 nested loops. It's enough like matrix multiply that you can use the same ideas to get a 6x speed up there. Gaussian elimination, the n-body problem, tall skinny QR, which is solving a very overdetermined least squares problem, symmetric eigensolvers, and then the mini GMG benchmarks. This is a very different kind of iterative scheme where we're running multigrid, and it's the bottom solve, the iterative solver at the bottom solve that's actually the benchmark, and we get big speedups there. So I'm going to give you an overview of all of the ideas behind these speedups. Now, you don't have to take my word for it that this is a good idea. You can take the word of someone at a higher pay scale, say President Obama. And so here's a quote from the DOE budget request for the 2012 budget. And one of the lines in there about of highlights was, on modern computer architectures, communication takes longer than the performance of a floating point arithmetic. So what you need to do is minimize communication between processors in the memory hierarchy by reformulating the communication patterns. And this referred specifically to some work in the Trilinos project. And so we talked to Mike Haru, and he said, well, what they were really referring to was the algorithms from your group that Mark Homan did in his PhD thesis, who's now a staff person in Trilinos and has put all these ideas in there. And I'm going to tell you about these algorithms. So that includes the communication avoiding GM-res, iterative algorithm, and the tall, skinny QR decomposition. So here's the outline of the talk. I'm going to survey the state of the art of communication avoiding algorithms. I'll sort of do maybe a little bit of a deep dive into matrix multiply, since that's the easiest to understand. And then I will tell you, how do you optimize that? And that's been known for the sequential case since at least 1981. So that's sort of a review. Then I'll tell you how to generalize that and actually go a lot faster. And I'll do that for tall, and it's going to be called 2.5D matrix multiply. That 2.5D, the name comes from the shape of the processor grid. I'll tell you about tall, skinny QR, solving least squares problems. And then it actually extends beyond things that sort of smell like three-nested loops to other schemes which are even faster, which is like Strawson's method. So it turns out that the ideas that we have to make this work for anything that not just smells like three-nested loops. I'll have a careful mathematical definition of what smells like three-nested loops means. Your intuition's perfectly good. But it actually works for anything that smells like loops. And we have an extension to things where you can have sort of generally arbitrary loops, and we can write down communication lower bounds, and in many cases, corresponding optimal algorithms. Then in the third part of the talk, which is, I'll talk about Krylov subspace schemes for sparse matrices. That uses a different set of principles. And then, if there's any time left at the end of the third hour of my talk, there's some related topics like how do you get the same answer every time you run the program. So we'll see how far we get through this outline. So let me go for surveying the state of the art of communication avoiding linear algebra. So let me tell you what the status is for direct linear algebra. So we have lower bounds on communication for anything that, like solving least squares problems, solving linear systems, solving eigenvalue problems, solving the singular value decomposition. So, and it's all pretty much the same lower bound, because there's one theory that sort of covers all of these. And what you do when you get a lower bound first is you compare it to the existing libraries like LAPACK and ScalaPACK, and you ask, are they good enough? And the answer was no. They almost always did asymptotically more communication than necessary. And so we've been busy for quite a while now trying to add these to libraries, including the ones I just mentioned in Plasma and Magma and other ones. And as you'll see, there's very large speedups that are possible. And now what the theory does is it gives you a design space, right? Being theory, it doesn't tell you exactly what all the constants are. And so what we use is some auto-tuning after that to sort of search the design space of possible algorithms that could be optimal, and then figure out exactly what the blocking sizes are and all those parameters to make it really work well on a particular machine. And so that's the summary of direct linear algebra, and it's sort of ditto, the same story for iterative linear algebra. So let me go back now to the direct stuff and tell you what the lower bound is. And so imagine now I have just two levels of memory hierarchy. I have a big DRAM, and I have a little memory of size capital M, which think of as your cache. And I want to execute an algorithm. It's going to perform a certain number of floating point operations. And I want to know how much data do I have to move back and forth between my fast memory of size capital M and the DRAM in order to execute it. So it turns out that as long as it smells like three-nested loops, the number of words that have to move back and forth between fast and slow memory is lower bounded by some constant multiple of the number of flops it's assigned, divided by the square root of the cache size, the fast memory size. So that's true for anything that smells like three-nested loops. Now, in the parallel case, how do I interpret this? So imagine now that this is one processor. And I'm asking, how much does this one processor have to move between its local memory, M is the local memory now, and all the other memory on the machine, all the other processors? That's the slow memory. It's the same lower bound. You ask, how many flops have I assigned to that processor, 1/5 of the total if it's load balanced, and that's its local memory size. It's the same lower bound. So this holds for matrix multiply. That's been known for a very, very long time for the sequential case. And now we know it holds for just about everything. It holds for the basic linear algebra subroutines, for LU decomposition, for QR, eigenvalues, SVD, tensors. Now, tensors are more than 3 loops, because you can have many, many dimensions, but it's the same idea. it actually holds for some whole programs. You can have sequences of these operations. If you want to compute the power of a matrix, you can do many matrix multiplies. That whole sequence, the same lower bound applies. It works on both dense and sparse matrices, so the number of flops doesn't have to be n cubed. It can be however many flops you do for your particular sparse matrix. You may not know until the end of the algorithm how many you've done, but the lower bound still applies. It's both sequential and parallel, and it applies to some graph theoretic algorithms, because there's no reason I have to do multiplies and adds in the inner loop. I can do maxes and mins and things like that. It just depends on what data you access, and that's what you do inside graph theoretic algorithms. So that's the lower bound on the bandwidth. How about the lower bound on the latency? So here's the simplest thing you could imagine doing. We'll have a better bound later. How many messages do I have to send? Well, just imagine I take all the words and I pack them into the largest possible message. That tells me the fewest messages. So what's the largest possible message you could send? It's the whole memory, capital M. So my lower bound of the number of messages is just going to be a factor of m smaller than that one. That's going to be my goal I'm going to try to attain, which I will for some algorithms. And I'm pleased to say all this won a Best Paper Prize a few years ago. So given all these lower bounds, what we do, as I said before, is we're going to compare them to LAPACK and ScalePACK, and they do not attain the lower bounds. So we've been busy inventing new algorithms, and there are new algorithms for pretty much everything, and all pair shortest path as well. So what do I mean by new algorithms? I mean they have new numerical properties. I can't use exactly the same algorithms as before. So for example, we can't do partial pivoting. When you do Gaussian elimination, we have a different kind of pivoting that is still, we had to prove it was numerically stable, and that attains the lower bound. We have new ways to encode the answers, so the output of a QR decomposition is not going to be represented by the usual bunch of householder vectors. It's going to be represented in a different way, but it still is a perfectly good representation. And so that's new data structures as well. And of course, we also have to do loop transformations. We have to do all the operations in a different funny order, but that's not enough. We need new algorithms as well. Now, we've made the most progress in dense linear algebra because that's the most structured, but we've also been working on sparse linear algebra. And so I won't say too much about that for lack of time, but there are classes of sparse matrices. You have to have some assumption about the sparsity structure in order to make progress. So for example, sparse Cholesky on a matrix with decent separators, like finite element problems, the theory applies and lower bounds are attainable. And so there's just lots of work in progress. Okay. So now, let me go back to just matrix multiply, in fact, sequential matrix multiply, and remind you, if you haven't seen this before, of how you attain the lower bound, and then generalize that. So here is the simplest possible algorithm you could imagine, 3 nested loops over I, j, and k, and in the middle, I'm going to do the obvious thing. I'm going to multiply a, I, k, b, k, j, and update c. So here's a picture to illustrate what's going on. Here are my matrices. And what is the inner loop doing? It's taking the dot product of the ith row of A, which I've colored in, the jth column of B, and it's updating the ijth entry of C. So that's the code. Let me annotate it now so we know how much it communicates. So I'm just going to put in some comments that indicate where the data moves, because that's not explicit in the code. So here, I'm going to read in the first row of A into fast memory and keep it there, because I'm going to use it over and over again. Then, in the next loop, I read that guy in, because I now know I and j. And I also need to read in the jth column of B so I can do the dot product. And then the inner loop, all the data is there, and I can just do that dot product. So there's no data movement there. And then I write C back to memory. So now, let me just count how much data did I move for this kind of obvious algorithm. I read each row of A exactly once. That's the lower bound. I have to read the whole matrix in once, so that's n squared reads. Can't do less than that. I read each entry of C and wrote each entry of C exactly once. That's obviously a lower bound. But I read the whole matrix B in n times. So it came out to a total of n cubed reads of the matrix B. And so I'm doing as many reads as I am doing arithmetic almost, right? I'm doing n cubed reads of the matrix B and 2 n cubed arithmetic. They're proportional. And since a read is so much more expensive than a flop, it's going to, this is a terrible algorithm. It's going to be very, very slow. So what is the well-known way to fix this? I'm going to do a blocked version of the algorithm. And so I'm going to break my matrix up into B by B blocks. So that little blue square is not a 1 by 1 entry. It's now a B by B entry. I'm still going to have 3 nested loops, but I'm going to loop over blocks. So I'm going to loop over, over blocks. I'm going to read in this block. Then the innermost loop is going to read a B by B block of A, a B by B block of B, and then I'm going to do a B by B matrix multiply. So this inner loop is actually 3 more lines of code. It's doing a B by B matrix multiply of that matrix times that matrix to update that one. And the idea is if all these 3 blocks fit in fast memory, there's no more memory traffic during the inner loop. And so I can hopefully save something there. And so let me just do the counting again, see if I came out ahead. It turns out I read the matrix C exactly once, as good as before, hits the lower bound. I write C once, but now I'm going to read and write A and B less often. And if you do the arithmetic, it turns out I'm going to read them not n cubed times, but n cubed divided by b. So I'm doing fewer reads and writes by a factor of b. And if I pick b large, then that may be much, much smaller than the amount of arithmetic. So let me now ask, how do I pick b? So the idea is, what did I assume that I could fit 3 b by b blocks in cache and then do a b by b matrix multiply? So that means, and if I do that, then I hit this particular value, n cubed over b reads and writes. So I want to make b as big as possible to make that as small as possible. How big can I make b? 3b squared has to fit in cache. So b is about the square root of m. And so that tells me I'm doing about n cubed divided by m to the 1/2 reads and writes. And that attains the lower bound. And this has been known since 1981 at least. So all this assumed is that I knew the value of the cache size. And of course, if I have many levels of cache, which I almost certainly do, I have to have not just 6 nested loops, I'm meaning 9 or 12 or something annoying like that. And so there turns out you can generalize this. There are things called cache oblivious algorithms, where you just write the algorithm recursively. You say, I'm doing n by n matrix multiply. That's really 8 matrix multiplies of half-size matrices, n over 2 by n over 2. So you just write it recursively, and you can still hit the lower bound, and you don't have to write annoying code like that. So that's the sequential case. Let me now go on to the parallel case, just in one slide, remind you how to hit the lower bound. And this is an algorithm called summa, which has been reinvented many times. So here's a picture of how it works. So suppose I have an n by n matrix, and let's just suppose I have 16 processors, p equals 16. I'm going to arrange them here in a 4 by 4 grid. And so each processor is going to own a n over 4 by n over 4 submatrix. So each block here represents a submatrix and a processor. So at each stage, what am I going to do? Well, mathematically, I need to take each column of A, or each block of columns of A, multiply it by each row or block of rows of B, and update the matrix. So think of it as kind of an outer product formulation. So what is the communication pattern? The processor that owns this chunk of A, so 1/4 of the rows and a bunch of columns, he's going to broadcast it sideways. So all these black arrows means please broadcast. So all these processors get a copy of that red submatrix. All of these processors get a copy of that blue submatrix, so that processor broadcasts down, and every column is broadcasting at the same time. So then each processor gets a copy of a blue submatrix from a neighbor, a copy of a red submatrix, and then it does a local matrix multiply to update the green. Multiplies red times blue equals green. And if you do all, so that's a very simple algorithm, and if you do all the counting, it hits the lower bound using the minimum amount of memory. So let me now just tell you what the lower bound is and how we attain it, not just for matrix multiply, but for, yes, question?
So basically, to improve the performance of a matrix vector multiplication, you would typically use a block matrices.
So it turns out that for matrix vector multiply, you are doomed. You can't, because the amount of data movement is you can't do less than kind of the obvious, n squared kind of data movement.
Well, because you had one example.
And the reason is that there's no reuse, right? Every entry of the matrix is used exactly once. It participates in one matrix vector multiply, and the only way you can possibly minimize communication in a more than a constant sense is if each number can participate in more than one many operations, which is certainly true for matrix multiply. So that says that your algorithm has to be BLAS3 or something that's doing n cubed operations. BLAS2, you can't do anything. Yeah, so that, I mean, you can make constant improvements, but you can't make these kind of asymptotic improvements where you have something like an m to the 1/2 in the denominator. So, yes. Yes?
If we have higher latency operations like divide instructions, do I need to just replace that flops by the cost of those operations?
Yes. Yes. So I'm hiding a lot of constants in here, and there's a lot of papers which do the details. But the difference between a divide and a multiply and an add is sort of hidden in the cost of a flop. Okay. Yes. Okay, so let me just say what is the general case in parallel. So I'm going to assume, not just for matrix multiply, which was the last slide. So I assume I have n by n matrices. I'm going to work on p processors. And so remember, there's an m in the denominator of my lower bound. I have to pick m. So let me just make the reasonable sounding assumption that I want to use as little memory as necessary. So I have a total, if I have n by n matrices and I have p processors, each processor is going to get n squared over p. So that's the local memory. So the lower bound says it's the number of flops, n cubed over p. Everybody is, it's load balance, divided by the square root of m, plug in that formula, and there's the lower bound, n squared divided by the square root of p words you have to move. And the number of messages is a factor of m lower, and that's the square root of p. And so those are the lower bounds. That's attained by the matrix multiply algorithm I just showed you there. And in fact, what we did is we looked at scale-a-pack, and we asked, are we close? And it turned out that for the number of words moved, it almost always hit that lower bound right there, except for the eigenvalue problem. That was asymptotically worse. But for the number of messages, it was almost always asymptotically worse. We sent many more messages than were necessary, except for Koleski. And so our first thing that we did is we found new algorithms for all these things that hit that lower bound to within some like log p factor or log squared p factor. And so now we do have optimal algorithms for all of these. I should say that the only algorithm we know of for the non-symmetric eigenvalue problem that it hits the lower bound is randomized. We don't have a deterministic algorithm. It has to use randomization. So that's an interesting open question. But then we asked ourselves, can we do better? Can we do better than hitting that lower bound that I just told you about? So that seems like a funny question. How can we do better than hitting a lower bound? And the answer was I had an assumption. And the assumption was that I used as little memory as possible, which was that there was only one copy of all the data in the machine. Everything was n squared over p. But m is in the denominator, and the lower bound is still true if we use more memory. So the question is, can we attain it? And I wouldn't ask the question if the answer were no. So there's a special case that's been known for actually a long time, and it's being reinvented over and over again, which is why I have all these references. It's called three-dimensional matrix multiply. And so instead of arranging your p processors in a square root of p by square root of p grid, what they did is they arranged them in a cube root of p by cube root of p by cube root of p cubed, and they assumed that they had enough memory to copy the matrix cube root of p times in order to communicate less. So if you have 1,000 processors, that means you'd need 10 times as much memory to run this algorithm. And it's not always in the cards that you have 10 times as much memory. We would like to be able to do something clever no matter how much memory you have. So let me tell you how to do that. And I'll tell you on one slide how it works for 2.5-dimensional matrix multiply. And we call it 2.5-dimensional because we're going to take our p processors and arrange them in this kind of 2.5-dimensional shaped grid. And so I have a parameter, and the parameter is how many copies of the data can I afford. So can I afford c equal 2 copies, c equal 3 copies, depends on how much memory I have. So given that, I lay out the processors in this particular grid. And so this is what it would look like if I had 32 processors and could afford 2 copies. And let me just, to write down the algorithm, index the processors in this particular way. And I'm going to assume initially that all my data is on the top layer. So this processor owns an n over 4 by n over 4 submatrix of A and B and so forth. So what does the algorithm do in 3 lines? Every processor on the top layer is going to broadcast its copies of its submatrices down. So I'm going to have a copy of a redundant copy of the matrix on every layer. Here, so I'll have 2 copies. So that's where I need the extra memory. Then the second step is each layer runs 1/7 of that summa algorithm I told you about. So here I run 1/2 of that optimal algorithm. What do I end up with? I end up with 1/2 of all the partial sums that I need on each layer. So in other words, I've computed half the sums on this layer and half the sums on that layer. And the final step is I do a reduction. I just combine all the partial sums vertically, because they're all aligned up in the right place, and the actual true answer appears in the top layer. And so that's a very simple algorithm. And the question is, how much speed up can I get from doing this? Well, how about a factor of 12? So here's an example where I can get a 12x speed up. So this was an experiment where on an IBM BGP with 64,000 cores. And I did it for 2 matrices, a small one, 8K by 8K, which is a tiny matrix to multiply on 64,000 cores. It seems like a waste. And then a much bigger matrix, 131K by 131K. And the vertical axis is percentage of peak, percentage of floating point peak, if communication were free. And I have two vertical bars, one where I run the 2D algorithm, so minimal memory, and one where I run the 2.5D algorithm, where here I could afford to use 16 copies of the matrix. The matrix wasn't very big. If I run the classical algorithm, it runs at 5% of peak, so it's really a waste to use all those cores. But if I'm willing to use 16 copies, I can go 12x faster, and I'm up to like 25% of peak. And so that's worth doing. Now, what about the bigger matrix? I only get a 2.7x speedup. And that's because this problem is much more compute-bound and less communication-bound. But let me do a breakdown of where this speedup came from. So this is the same run, but I've broken it down into how much time was spent communicating versus idle versus actual flops. And now, so again, I have the 8K problem, the 131K problem, and the 2D, and now this is the 2.5D where I replicate. And the vertical axis is the execution time normalized by the 2D problem. So here you can see that half the time is spent in communication, and it drops by 95% when I do the replication. But there's also all this idle time waiting for stuff to show up, and that also almost nearly disappears. And so there's where I get the 12x speedup. Here, the flop time, the green part, doesn't change, and so that's why I only get a 2.7x speedup. But still, most of the communication went away. So if this is where all your energy went, I still may have saved you 95% of the energy, but not the time. Now, notice here, even the flops went faster. The green bar is the flop time, and that dropped significantly. But I'm still doing the same flop. So how could that be? It's because the local BLAs 3, are being called on larger submatrices when I do the replication. So the local BLAs 3 are running faster, which is why that's better too. So that's the story for matrix multiply, and I'm pleased to say this won a best paper prize, another one. So now let me use this idea to tell you about perfect strong scaling. So what is the ideal goal that we would have when you implement an algorithm? You double the number of processors, and it runs twice as fast, right? So let's see if we can actually do that. And let me ask the same question about energy. So the idea here is that if you double the number of processors, you get twice as many resources, but not just twice as many CPUs, you get twice as much memory. So what you want to do when you double the number of processors is use all that memory that's available to you too, and see how much faster you go. So let me start, I'm just going to write down some formulas with a minimal amount of memory. So I have P processors, each one has a local memory of size M, so the total memory is just big enough to fit 3 matrices. And I'm going to increase the number of processors by a factor of C, and I'm going to increase the total memory by a factor of C, and I'll use it and see what the formula says, the runtime. So I'm going to write down kind of a messy formula. We're just going to care about how it scales. So I'm going to count the number of flops and multiply by the seconds per flop, the seconds per word moved, and the seconds per message. And there it is. This is the time it takes to run the problem on C times P processors. And it's a little messy. All I care about is how it scales, and it scales perfectly. When I increase the number of processors by a factor of C, the flop time goes down by a factor of C, the bandwidth time goes down by a factor of C, and the latency time goes down by a factor of C. So that's what I mean by perfect strong scaling in time. Now, what about energy? We've done some careful energy modeling, and so now this is sort of a collaboration with a bunch of architecture colleagues who say, yeah, this is a reasonable model, because architectures are complicated. The energy goes to lots of places. So we're going to count the joules per flop, the joules per word moved across the network, the joules per message. But that's not the only place you burn energy. The memory burns a lot of energy. So I'm going to count the joules per word of memory used per second, right, just to keep the thing alive. And then there's the leakage and the fans and everything else. So I'll just throw in another term, which is the joules per second for everything else in the computer. So then we can write down an even longer, messier formula for the energy that it takes to run an n by n matrix multiply on C times P processors. And the question is how it scales. And the answer is it scales perfectly. It takes no more energy to solve the problem C times faster. Now, how could that be? So the answer is I have C times as many processors. They're all burning the same power, and they're burning at exactly 1 cth as long, because I get perfect timing speed up. And so the total energy is constant. And so that's perfect strong scaling in energy. And this extends to n-body and Strawson and lots of other algorithms too. And the other thing that we can do, I should say, is that we can ask, what network do you need to actually attain these lower bounds? Right? So I haven't made any assumptions about the network, and obviously supercomputers are built with many different kinds. We can actually prove lower bounds on what the network connectivity is to attain these lower bounds. And it turns out that you need a 3-dimensional torus at least. And a two-dimensional torus is not enough. Fortunately, most people build 3D toruses these days, or something even better. It turns out for Strawson, you need at least a four-dimensional torus. So you can, all those lower bounds exist too. So now, let me leave matrix multiply, finally, and say something about another algorithm, which is the same story for Gaussian elimination. And as I mentioned before, there are different ways you can run it. You can run it, so I have a bunch of experiments here. I've run it without pivoting. That's sort of cheating, but it's certainly the fastest thing you could imagine. And then I've thrown in pivoting, but it's not partial pivoting because that does not hit the lower bound. It's what we call communication avoiding pivoting, CA pivoting. And so this is the best way we know how to do it. It attains the lower bound asymptotically. And now we get speedups on the around a factor of 2. And again, it's because the communication goes down significantly. Now, we tried for quite a while to get the same perfect strong scaling for Gaussian elimination as for matrix multiply. We wanted not just the bandwidth cost to go down by a factor of c, we wanted the latency cost to go down too. And we tried, and we couldn't do it. And so what do you do when you can't invent an algorithm? You prove a theorem that says it's impossible. You prove a new lower bound. And so here's the new theorem. It says that perfect strong scaling is impossible for algorithms like Gaussian elimination, which have more dependencies in them, obviously. You don't have as much freedom to reorder the operations as you do in matrix multiply. Matrix multiply, you can do anything in any order. It's fine. Gaussian elimination, you sort of have to go from the top to the bottom. And for algorithms like that, the theorem says that the latency times the bandwidth, no matter how you organize it, no matter how much memory you have, is lower bounded by n squared. So if I make the bandwidth go down by some factor, the latency has to go up. And you just have this natural trade-off. And so if you want to minimize latency, it turns out that one copy of the data is the best you can do. OK, so that's enough of that. I want to go on now to a different topic, which is tall, skinny QR. So this uses a different kind of principle. And so I want to compute the QR decomposition of a tall, skinny matrix. And so I'm going to sketch what the algorithm looks like here first. So imagine I have broken up my matrix into 4 different blocks. Because only perhaps each processor is going to get a different subblock of this. So then what each processor does, without any communication at all, it does a local QR decomposition just on the data it owns. Okay? So no communication there. Now, what have I done implicitly? I've implicitly factored my matrix into the product of this block diagonal, still orthogonal matrix times this stack of 4 triangles. That's not the QR decomposition, but it's progress. Then what I do is I take that stack of 4 triangles, break them up into pairs, and take each pair and do its local QR decomposition. And what I've done now is factored those 4 triangles into the product of this block diagonal orthogonal matrix times half as many triangles. And then one more step, I take the last 2 triangles and I do their QR decomposition, and I get 1 triangle. And that R sub 0, 2, that is the R from the QR decomposition. So what I've done then is I factored my matrix into the product of that orthogonal matrix times that orthogonal matrix times that orthogonal matrix times R. That's my new data structure for the QR decomposition. And the output is just the individual Qs that come from that factorization, and their classical data structure is times R. So what I've done now, let me now just repeat what I've said here. This is sort of the optimal algorithm. And what I've really done is I've called MPI reduce, where the reduction operator is a QR decomposition. That's all I've done. It's a nice, simple binary tree, and I just pass R's up the tree, and out comes the R at the end. And then I save the Q's on the way. So that's and that's one reduction, and you can prove that hits the lower bound. So that's the optimal parallel algorithm. Now, what about an optimal sequential algorithm, where my matrix is too big to fit in cache? It's exactly the same algorithm. I just use a different reduction tree. So here is the optimal algorithm for a sequential machine. Suppose I can only fit a quarter of the rows into cache. I'll bring in the first quarter of the rows, do a QR decomposition. Bring in the next quarter of the rows, stack R0, 0 on top of W1, do that QR decomposition. Bring in the next quarter of the rows, and so forth. And by the time I'm done, I've read this matrix from slow memory to fast memory once. And 1 is a lower bound on communication, right? I have to read it at least once, and there it is. Now, what if I have a slightly more complicated machine like dual core? So I'll bring in the first 2 blocks, do their QR decompositions in parallel, combine them, and then have sort of this other reduction tree. Now, but what if I have a real computer? It's multi-core and multi-socket and multi-rack and multi-site and out of core. I'm just going to choose a reduction tree dynamically depending on what hardware resources I happen to have at the moment I call the subroutine, right? Which could vary every time I call it. So I will get a different data structure every time I call it, perhaps, but it's still the QR decomposition, and you can still do anything with it that you want. So what kind of speedups do we get for doing this? Well, some of these are older and some of them are newer, up to an 8x speedup on an 8-core Intel Cloverton, 6.7x on this pretty old Pentium 3 cluster, 13x on a GPU. This was an interesting one. This is grid computing, so this was QR decomposition on 4 computers in 4 French cities connected over the internet. So latency is the cost there. And it was exactly 4 times faster than doing it on 1 city, so that's the best speed up you could imagine. And we also have a cloud computing interface. We first did this on a cloud structure that was at another university, and now it's in Spark. So we just released it in Spark, so if you've used that, which is widely used in industry, you can download it. The algorithm's available there too. And it basically is the same cost as 2 map reduces. So you just call map reduce twice, and it sort of has the same cost as that. So that's sort of almost minimizing the cost. Now, the best speed up we got in the sequential case was infinite. So what does that mean? I had a student run this algorithm on his laptop, and it was too big to fit in DRAM, right? So the classical algorithm kept thrashing the cache, and he finally just hit Control-C because he didn't want to keep waiting for it. In contrast, the new algorithm was only 2 times slower than as though DRAM were infinite. So it almost completely hid the disk access time. So that's a good speed up. Now, if you're doing the SVD of a tall, skinny matrix, this is all there is to it, right? Because you get the little r at the end, and then you do the SVD of the r, and that's very cheap compared to that. So hopefully this will be in the next LAPACK release, too. We're finally getting to that. So just to sort of summarize all this, work on direct linear algebra, there's lots and lots of other algorithms. Symmetric indefinite factorizations, pivoting is very complicated if you have QR with pivoting eigenvalue problems. We have work on different kinds of sparse matrices, but also structured matrices. Laurie mentioned HSS, hierarchically semi-separable, sort of similar ideas apply there, all pairs shortest path. And then using minimal memory, 1 copy of the data versus multiple copies of the data. And there are all these different platforms that you want to apply these to, because where the communication appears is different, whether it's cloud or heterogeneous or GPUs, and integrating this into lots of different packages and also applications like tensor contractions. So that's classical linear algebra. And I just wanted to say one more thing in case people are saying, well, no, there is a faster matrix multiply out there. It's called Strawson. What can you do about Strawson? So let me just tell you, it all extends to that kind of stuff. So let me just compare in one slide what the old lower bound was that I just told you about and compare it to the new one. So this is the lower bound that I had before. It's the number of flops divided by the square root of the local memory size. And I've just written it in this funny way. So all I have to do is you see a 3 there, and you see a 3 there. So what's the lower bound for Strawson? All I have to do is change the 3 to log base 2 of 7. Now, the typesetting is much easier than the proof, but that's all that's how it all extends. So we do asymptotically fewer flops, and we do similarly asymptotically fewer communication too if we implement it right. And it's not just Strawson, it applies to Strawson-like algorithms. And again, I just changed log base 2 of 7 to whatever that magical exponent is, and people are still looking for the minimum. Been doing that for a long time. So, and the proof is very different from what I had before. It's graph expansion stuff. And what do I mean by Strawson-like? There are some technical restrictions. You can read the papers about it. Now, does this continue forever? No. It would be kind of magic if I could just keep adding memory and get an infinite speed up. But all of this has a limit. Here's how much memory you can use before you hit the lower bound. And more memory does not make you go faster. And this is true for all of these guys. N squared divided by the number of processors to that magical exponent. So in the case of classical matrix multiply, it's n squared over p to the 2/3. That's how much memory you can use. That's the hard limit, and everybody else enjoys the same limit. And this also won a best paper prize. So it's natural to ask, is this lower bound attainable? So let me show you some speed up plots. And so here are a whole bunch of different implementations of a very large matrix multiply, 94K by 94K, so fixed size, on Franklin. A Cray XT4 for many different processors, and the vertical axis is the effective gigaflop. So I'm going to be comparing classical matrix multiply to Strawson. So how do I do that fairly? I'm going to take 2n cubed over p divided by the time. So up is good, and so the vertical axis is basically inversely proportional to runtime. So up is good. And so here's classical matrix multiply. It's running at, at this speed, pretty flat. There's the peak speed of the machine, that dotted line, so it's getting half of peak. Here's 2.5D matrix multiply. Again, classical n-cube matrix multiply. It's getting much closer to peak. These blue lines are previous attempts people have had to parallelize Strawson. They haven't, sometimes they're faster, but not always. And here's our new algorithm. And it's running faster than peak machine speed, as it should, because it's doing a lot fewer flops. And it's almost a horizontal line. That means we're almost getting perfect strong scaling, which is what the theory predicts. And so so we can make good use of these theoretical algorithms. And I'm pleased to say this was invited to appear as a research highlight. OK, so let me say that's the end of sort of classical linear algebra. I want to now go beyond that, but are there any questions before I do? Yes?
So you had a few plots which portray the times, like you broke it up into computation time, idle time, and communication time. How exactly do you quantify?
So the question is, where did we put the timing calls in the code? That's sort of what we had to do, right? We had to put, call timer at various places and break down the code into different parts along the critical path. So the thing is, each processor is doing something different. And so what you have to do is say, what is the critical path of the algorithm? And then put the timing in there. So that, I believe, was measuring the times broken down along the critical path.
You just manually put in like the...
Yes. Okay. Right. This was all,
So there's no like algorithm, or you didn't like do this by paper, did you?
Well, we had our theoretical predictions, but then that breakdown was actual, real data by putting in timers into the code. Yeah, as I said, the theory doesn't, leaves out a lot of constants. Real machines are much more complicated, so you got to measure it. Yeah.
How about the energy?
So we are collaborating with a whole bunch of people in a lab at Berkeley who are, architects and building tools to measure energy more carefully. I had a student spend a summer at Intel working with their energy measurement tools, and let's just say they weren't quite debugged yet. I don't know. Can't say any more. And so it's still an open question as to how to get good energy measurements. So I'd say that's current research.
Is there a library or something out there now that we
So Intel has a tool where they use their performance counters and then compute certain linear combinations of them, assigning joules per this op, joules per that op, and they try to estimate the energy for you. But a lot of it's still approximations. There are a lot of lower level tools if you have Verilog or something like that, where you can actually get more detailed energy counters, and I can give you a pointer to lots of papers, but. Yeah, that's an offline discussion. So the architectural community is working on building tools, very hard right now. Okay, so yes?
So I'm just wondering, where your matrices come from real application or just some artificial matrices for your test case?
So this was all dense linear algebra, so I could put in any numbers I wanted into the matrices. It wouldn't change their performance at all. For the sparse stuff, then the sparsity structure depends very much on the entries, on where the stuff comes from. And so we have a mixture of theory where we make some theoretical assumptions about the sparsity structure, and then we have some more real matrices which come from various kinds of grids and so forth. But I'm not showing you that data in this particular talk yet. I'll have some more real data later when I get to Krylov methods. I have lots of real matrices there to do tests on.
So this algorithm only works for dense matrices.
So far. Well, I didn't have time to tell you about the sparse versions, but there is work on sparse. All this stuff applies to sparse linear algebra, and we have ongoing work to do that, and some implementations. But the sparse stuff is going to be mostly in this section of the talk on Krylov methods.
Okay. So do you already have some packages? Implemented your algorithm?
Well, we have prototypes, and we're currently trying to get it all into LAPACK and ScalaPACK and Plasma and Magma, and it's sort of in process. So let me just sort of say how this all generalizes to arbitrary code. So here's my optimal sequential matrix multiply, starting with naive code. And as I told you before, that what we're going to do is break it down into B by B blocks. And so if I break it, I loop over all B by B blocks. In the innermost loop, I do that B by B matrix multiply. And the theorem, this is just a reminder from the beginning of the lecture, is that if I pick the right block size, which happens to be square root of m, then I can fit all those blocks into fast memory. And the lower bound turns into n cubed over m to the 1/2. And that all was very specialized to matrix multiply. Now what I want to do is generalize and say, can I write down a general theory so that no matter what code this looks like, I can tell you what 1/2 becomes, okay? So here's the theory. So there's the code, again, for matrix multiply. It turns out that all I need to do everything I need to know about this code, I can encode in this one little 3 by 3 matrix, where there's one row for every array, one row for every loop index, and a 1 or a 0 indicating which array has which subscript. So A is indexed by ik, so I have a 1 there and a 1 there, right? That's all I need to know. Then the theory goes on to say, you need to solve a little 3 by 3 linear program with this matrix. And the linear program says, please maximize the sum of this 3 vector, subject to the constraint that this matrix times x is less than or equal to 1. And what is the answer to this trivial linear program? 1/2, 1/2, 1/2. And the value is 3/2. And I'm going to call it S sub HBL. HBL is the acronym for 3 famous mathematicians whose work this depends on. So finally, after you do all that, the theorem says that no matter how I reorganize this code, the number of words moved is lower bounded by the number of flops, n cubed, divided by m to this magical exponent, the solution of the linear program minus 1. That's where that 1/2 comes from. And how do you attain it? You have to block it. What are the optimal block sizes? It's m to the power of these exponents that are the solution of the linear program. So it's m to the 1/2, m to the 1/2, m to the 1/2. Now, that's matrix multiply. Let's try a different algorithm, because I claim this works for anything. So let's try n-body. So here is an even simpler code. It's 2 nested loops. I take every pair of particles, pi and pj, and I compute something, some interaction, and I update a force vector. Everything I need to know about this algorithm, I embed in the same little matrix. There's one row for every array, and these are different because I'm indexing them different. One column for every loop index, and then 1s and 0s. And the theory is the same. Please solve a little linear program, maximize the sum of now just 2 x's, subject to that. And the answer is 1, 1, and the value of the linear program is 2. So the theory says that no matter how I reorganize n-body, I have to do at least n squared divided by m to the first power data moves, and it's attained by block sizes m by m. Now, not only does this theory tell me how to do this in the sequential case, it generalizes 2.5D matrix multiply. So all those tricks that for 2.5D matrix multiply, it extends here too. So let me try it. Let me try to make n-body go faster by replicating the data. And so here are the speedups, and they're up to a factor of 12 again. And so what I'm going to do is this is 32,000 particles on 8,000 cores. It seems like way too many cores to try to parallelize n-body for 32,000 particles, because that's only 4 particles per core. And indeed, if I run it with 1 copy, then the green is now the communication, and it totally outweighs the flops. But by the time I'm willing to make 64 copies, and 64 copies is peanuts because it's only 4 particles per processor, the communication has gone away, and I get perfect speed up. So 10 minutes, OK? So here are some applications, just to remind you. So people have been doing this for a long time for gravity and turbulence and molecular dynamics. And you might say, well, don't people use fast multipole? Well, yes, but they still use the direct n-body solver for the base case, right? You still use this for the local interactions, and this speeds up the local interactions. It's also used for, one of my colleagues uses it for electron beam lithography, designing things in Silicon Valley. But here's a new application I only learned about recently, and that's hair. So if you've ever seen a recent Disney movie with these characters in it, this is Princess Merida from Brave. All of their hair is done by an n-body simulation. And the code was written by one of Kathy Yellick's graduate students who spent a summer at Disney. And so it turns out that what they do is each strand of hair is represented by a particle. The interactions are the forces separating the hairs. So when she waves her head around and all the hair bobs, and as it does in the movie, it's all being computed by this n-body code. And so just remember that next. So it turns out he was only there for 3 months, and you don't get screen credit unless you're there for at least 6 months. Otherwise, his name would be on all these movies. But they've used it in every movie since then. OK, So now let me move on to some random code just to show you how general it is. So this is not a real example. It's kind of just for shock and awe. So I just sort of wrote down some random code. So I said, OK, 6 arrays, A1 through A6. They have a bunch of subscripts. I'll just make them up, 6 different ones, I2, I3, I5, whatever. Everything I need to know about that mess, I record in a 6x6 matrix, 1 row for each array, 1 column for each loop index. And I write down the same linear program. It's now a 6x6 linear program. And I solve it as before. And the answer is, no matter how I reorganize this code, I have to do at least n to the 6th divided by m to the 8/7 data moves. And 8/7 why? Well, that's what the theory tells me. And how do I attain it? It's m to the solution of the linear program, m to the 2/7, m to the 3/7, blah, blah. So that's not obvious from looking at that particular code. But that is the optimal one. So let me just say a few more words about where this theory comes from. It takes too long to explain all the details. So here's, again, matrix multiply. And so what do I need to know about it? All I need to know is that I have an inner loop, and I can index the inner loop iterations by a triple of integers, I, j, k. For every I, j, k, I'm doing something. And there's some subset of triples of integers that describes the algorithm. In this case, it's a cube, but it could be sparse, whatever. And I need to know that I'm accessing the locations just by these subscripts, right? I need to know what the subscripts look like. Now, what's the general case look like? I could have, here's an example. I could have an arbitrary number of nested loops, or it could be some recursive call. It doesn't matter. But I have some stuff in the inner loop, and it's just, all I need to know is who indexes whom. So here's the generalization. I can index every inner loop iteration by some tuple of integers, running over some subset of k tuples of integers. And I need to know that I'm accessing all these locations by these expressions. And I'm going to use the terminology from mathematics, group homomorphism. Now, why am I using that terminology? It's just to give you a hint of what math is necessary to do all the analysis. So it uses group theory and functional analysis and all sorts of different things. But these are just sort of linear expressions in the loop indices that tell me where to go find the data. And my goal now is that given any program that can be described this way, you're iterating over some tuples of integers, and you're accessing some array indices by these functions, give me a lower bound. OK. So in order to do that, I need to say, given a subset of loop iterations, how much data do I need to access it? And so I'm given a subset of loop indices I want to iterate. And here are the projections that tell me which data do I need. What I need to do is bound the number of loop iterations in terms of the number of entries of array A, array B, array C. So this is the cardinality of the projection. Okay? I know this is fast. So it turns out that to write this down, you need to write down a linear program. And here's the 3 famous mathematicians whose acronyms I used before: Holder, Braskamp, and Leap. So it says for all subgroups of zk, this particular linear program has to be satisfied. Rank of h, that's like the dimension of a vector space, except it's the same idea for groups. And all of these indices here, all of these variables S1 through Sm have to satisfy these linear equations. Now, it turns out that if you know that, there's a recent theorem by my collaborator in this work, Michael Christ at Berkeley, Terry Tao at UCLA, and a whole bunch of other pure mathematicians who were not thinking about computer science when they did this, that given S satisfying these linear constraints, then you can bound the size of this set, the number of loop iterations you can perform, given all the data. And there it is. This is a generalization of Cauchy-Schwarz, of Holder's inequality, every kind of inequality from functional analysis that's ever been invented, pretty much. And so putting it all together, what's the theorem? Given a program with array references given by these projections, choose these parameters to satisfy this linear program and to minimize their sum, then the number of words moved, no matter how you organize the algorithm, is lower bounded by the number of loop iterations divided by m, the cache size, to that magic exponent. And that sort of falls out of all this functional analysis. So the question is this bound attainable? I mean, obviously, for matrix multiply, it's attainable, and for n-body. But the first question we asked ourselves, for an arbitrary code, can we write it down, right? Because mathematicians said this exists. Why is it a question? Because there's for all subgroups, that's an infinite number of objects, right? So this doesn't even qualify as a linear program, which is a finite number of inequalities. So the first theorem we proved was bad news. that if you actually want to provably write down all the inequalities I had on the previous slide, it's equivalent to Hilbert's 10th problem over the rationals. Now, you may have heard of Hilbert's 10th problem over the integers. That is, given a set of polynomials with integer coefficients, can you decide if it has an integer solution or not? That was proven undecidable in the 1960s. So then there's Hilbert's 10th problem over the reals. That was proven decidable, Tarski decidable in the 1940s. This has been open for 40 years. Nobody knows if that's decidable. So that slowed us down for a while. But then we proved another theorem, which says that there's another linear program that you can write down, which is a subset of those constraints, and it is decidable, has the same solution, and so we can get the lower bound for sure. So now we can always write down the lower bound. The question is it decidable? Well, it depends on the loop dependencies. And if you have to be able to reorganize the code, and in the best case, like matrix multiply, you can do anything in any order, everything is fine. But so we've done a lot of examples, and it turns out that what you need to do is just write down the dual linear program. Take that linear program that comes out of that theory. Its dual tells you what the optimal tiling is. And in fact, that's the linear program I showed you for matrix multiply and for n body. So n 1/2, 1/2, 1/2 was the solution, and there's the optimal tiling. So there's a lot of ongoing work here. We're going to, we're trying to implement all this. We're collaborating with the compiler community because you don't want every programmer to have to learn functional analysis and group theory. It's enough to teach the compiler writers functional analysis and group theory. So we're collaborating with them to try to get this into compilers. We want to extend the perfect strong scaling, and because that all works too. And so that's work in progress. Now I have 5 minutes left, and so I'm probably just going to summarize the results here. And we'll see if people want more details. So let me just tell you how this is, so a completely different set of ideas. Avoiding communication iterative linear algebra. It turns out, so I'm going to imagine running your favorite algorithm like conjugate gradients or GMRes or Lanczos to solve AX equal B or an eigenvalue problem. What's the inner loop? It does a sparse matrix vector multiply, and it does some vector operations, right? And so that means that the cost of the algorithm is basically going to be the cost of k sparse matrix vector multiplies. And so our goal is going to be to minimize communication, because if you just do the obvious one and your matrix is too big to fit in cache, taking k steps will cost me k reads of the matrix from slow memory to fast memory. So let me assume the matrix is well partitioned. I mean, the ideas are more general, but just think, finite element matrix for now. So what about the serial case? The conventional algorithm, if I take k steps and my matrix is too big to fit in cache, every step I have to read my matrix from slow memory to fast memory to do my sparse matrix vector multiply, and so the cost is order k. That's the amount of data movement. We're going to do it with one move. I'm going to read the matrix once from slow memory to fast memory and take k steps of the algorithm, and one is optimal. Okay, you got to read the matrix at least once. This is a complete reorganization of the algorithm, of all of these algorithms. And so that's the serial case. What about the parallel case? So I have p processors. What's the conventional algorithm going to do? Every time it takes a step, I'm going to have to communicate with my neighbors, get some vector entries, bring them over, and do some dot products, right? Because all of these have some dot products involved. And a dot product is a reduction that costs me log p messages. And so I'm going to take k log p messages in order to take k steps of the algorithm. The new algorithm will do one reduction. It's going to do it in just log p messages, and that is optimal. And so let me just say that when you do all the details, there's lots of speedups possible, both modeled and measured. And the price is a little bit of redundant computation, but flops are cheap. That's the whole theme here. And so there's lots of challenges. If your matrix is not easy to partition, what do you do about it? Preconditioning is an important thing to do, and we can only do this for some preconditioners, not all. And maybe the most interesting problem is numerical stability, because even though our new algorithms give you the same answer as the old ones in exact arithmetic, in floating point, they have very different properties. So there's a lot of cleverness that's required to say what is a numerically stable way to do this as opposed to a merely mathematically correct way. So I'm just going to skip ahead and show you one speed up plot. So here's by CG stab. Old versus the new algorithm required a lot of reorganization. But here are the speed ups. And so this is for geometric multigrid and for a adaptive mesh refinement problem. And it turns out that most of the time is spent in the bottom solve, because by the time you get down to 4 unknowns per processor on many thousands of nodes, you can't keep refining. And so you're left with a problem which is a very sparse solve spread out over the whole machine. And the current thing that people do is they use a BiCG-stab to do the bottom solve. And so we improved that bottom solver by a factor of 4. The overall GMG solve got faster by a factor of 2.5. And we've put this into 2 box-lib implementations, a combustion code and a gas dynamics code. And the speedups aren't quite as good as for the model problem, but they're still good speedups. And it turns out that you don't usually think of the bottom solve being the killer, but it is in a lot of these examples. So just to summarize the iterative stuff, we have new lower bounds, optimal algorithms, and big speedups. There's lots of other algorithms that we've done that need to be done. So it's sort of an art right now to pick the numerically stable ones. But so that's work in progress. Preconditioning, that's hard, but we can do some, not always. And again, the code is complicated, so it's nice to use auto-tuning to generate it automatically. And I'll have to skip the related topics, where we can minimize writes separately from reads. So if you have non-volatile memory, we can get asymptotic speedups again by doing fewer writes than reads. That's very recent results. And if you're interested in getting the same answer when you run your program more than once, I mean, that's been gone for a while, but we have a new version of the BLAS which does guarantee reproducibility, and it runs just about as fast as a regular parallel BLAS. So we have a new release of that. For more details, we have a 155-page survey paper that you can get off of our website, which gives a survey as of 2013, so it's a little out of date. We have a live course which teaches this every spring semester, and it's all video captured, so you can listen to this at your leisure. And if you want to take it for real credit, you can get an account from NSF and do the online assignments. This is joint work with an awful lot of people. In particular, I'd like to mention Kathy Ellick, with whom I collaborate not just in avoiding communication, but raising 2 children. And of course, that sounds like a contradiction. You just have to be careful which communication you avoid. And so to summarize, it's time to redesign everything: linear algebra, n-body algorithms, software, and compilers. And what it all has in common is don't communicate